Every Rust developer has done it. Your code does not compile. The borrow checker is angry, and you just slap a .clone method on it. Problem solved, right? Well, maybe, but here's the thing most Rust tutorials don't tell you. Not all clones are created equal. Some are basically free. Others can destroy performance. Today we are going to learn exactly what happens under the hood when you call clone method, why some clones cost nanoseconds and while others cost milliseconds, and how to make smart decisions. So let's dive in. First, let's understand what clone actually is. Rust. Clone is a trait. When you call .clone on a value, you are asking Rust to create a completely independent duplicate of that data. But here's a key insight. Duplicate means very different things for different types. For simple integer like unsigned 64, duplicating means copying 8 bytes. That's one CPU instruction, literally free. For a string containing a million characters, duplicating means allocating a million bytes of a new memory. Then copying every single byte over that's expensive, right? And for something like arc, which is a reference counter smart pointer, duplicating just means incrementing a counter. The actual data stays exactly where it is. Same method name, widely different cost. This is what makes clone tricky. Let's start with the good news. Some types in Rust implement a trait called copy. These are types where cloning is so cheap that Rust does it automatically. Copy types include all your integers, unsigned integer, signed integer, all your floats, F32, F64, Boolean characters, and etc. are simple and simple tuples or arrays of copy types. When you clone a copy type, here's what actually happens at CPU level. It's a simple register copy. One instruction take about quarter of a nanosecond. So let's take this example where let a is equal to 42, which is unsigned 64-bit integer, and will again declare a variable called b, and we are taking b as a dot clone. This clone literally the same as just writing let b is equal to a. The compiler generates identical assembly, zero overhead. So if you are cloning integers or floats, don't even think twice about it. It's free. Now let's look at where clone gets expensive, strings and vectors. When you create a string in Rust, the actual character data lives on the heap. The string stuck on the stack just holds a pointer on that heap memory, plus the length and capacity also. When you clone a string, Rust has to call malloc to allocate new heap memory and copy every single byte from the original to the new allocation and return a new string pointing to this new memory. So as you can see, uh, let s1 is equal to a string which is allowable, and we are cloning string 1 into string 2. Now we have two completely independent strings, each with their own heap allocation. Modify one and other is unaffected. For a small string, this is fine, maybe 15 to 100 nanoseconds. But what about vector with 10 million elements? Let's look at this where we have declared a big vector which has type of unsigned 8-bit integer and has total 10 million elements. Just assume that, and we're copying that uh, big big vector into this copy variable. This single clone allocates 10 megabytes of memory and copies 10 million bytes. We are talking about 5 to 10 milliseconds. Do this in a loop and your program grinds to a halt. The cost of cloning heap allocated types scales with the size of the data. Small data, small cost, big data, big cost. So what if you need to share large data between multiple parts of your program? This is where ARC and RC pointers come in. ARC stands for Atomic Reference Counted. Instead of duplicating the data, ARC lets multiple owners share the same data through reference counting. So let's look at this. Let data is equal to arc.new, which has around 10 millions of record, and we are cloning on two different variables. So here's the magic. All three variables point to exact same 10 megabytes of data. When you call arc clone, Rust does not copy the vector. It just increments a counter that tracks how many owners exist. The cost, one atomic increment operation, about 1 to 2 nanoseconds. Doesn't matter if the data inside is 10 bytes or 10 gigabytes. I like to think of it this way. Cloning an arc is like copying a key to a house. You are not building a new house, you are just making another key that opens the same door. The data only gets fed when the last arc is dropped and the counter hits 0. But here's where people get tripped up. There are two ways to clone when you have an arc pointer, and they do very different things. So let's look at this where we are defining arc with um, string called hello, and we are cloning that arc string into uh, cheap variable, and we are cloning that same into expensive variable. See the difference. Arc clone clones the arc itself, just incrementing the reference count, but uh, expensive variable dereferences the arc first, then clone whatever is inside. In this case, it clones the string, which means a heap allocation. Same clone method, but one cost of 1 nanosecond. The other cost 50 to 100 nanoseconds. In a hot loop, that's 50 to 100 times more performative difference. This is why I recommend always write rclone method explicitly instead of arc.clone. It makes your intent crystal clear and prevents accidental expensive clones. The absolute worst place to put an expensive clone is inside a hot loop. If config is large struct with strings and vectors, you just created a million heap allocations. Your program will spend more time in the memory allocator than doing actual work. The fix, if you just need to read the data, borrow it. Or if you need shared ownership, wrap it in an arc pointer once outside the loop. Now you have one allocation total and a million cheap reference count increments. That's the difference between a program that takes 10 seconds and one that takes 10 milliseconds. So how do you decide when to clone? Here's my mental checklist. First, ask is this a copy type? If yes, clone freely. It's free. Second thing, can we borrow instead? If you only need to read the data, take a reference. It's zero cost. And third thing is, can we move instead? If you don't need the original anymore, transfer ownership. It's zero cost. Fourth thing is, do we need shared ownership? Use ARC or RC pointer. Clone is cheap. And fifth thing is this inside a hot loop? If yes, think very carefully. Consider borrowing or wrapping in ARC before the loop. And finally, is data small? For small strings or vector, cloning is often fine. Don't over optimize because readability matters too. The goal is not to eliminate all clones; it's to understand the cost and make informed decisions. Clone in Rust is a powerful tool, but it's not a magic. Behind that simple method call could be a single CPU instruction or a massive memory allocation. The Rust compiler won't stop you from cloning. It's up to you to understand the cost,